So I've been using PC emulators for code analysis purposes like forever. It's, I guess, since the 90s or so. Note the gray hair. Mainly because you can fiddle around with the hardware. You can do like silly little tricks or so. But QEMU actually plays a lot larger role than just for freaks like me or so who like to do code analysis. And so the addition of a virtual secure boot, I believe, is going to make a very, very big difference or so in things like cloud computing. The following talk by Gerd Hoffmann is going to be all about the trials and tribulations, I believe, of trying to get secure boot to actually work in QEMU and other systems. And that's really all I want to say about it. Please welcome to the stage Gerd Hoffmann.
Hello, I'm Gerd Hoffmann. I'm working for Red Hat for already 10 years around in the virtualization team, working on QEMU, both in user space, also on KVM on the kernel side. And one of my work areas is firmware, and that's why I'm giving this talk today. Oops, move that away. I first want to go over some terms which I'll talk about in this talk, and about how creating a plan when implementing something like secure boot for virtual machines. Then go over the implementations we had to do in all three involved software projects. And next, some hands-on session or some instructions if you want to play with that yourself, how we are going to do that. If there's enough time left, I'll go on with a short demo, and at the end, of course, questions and answers. So let's start with the terms. First one is, of course, secure boot. It's specified in the UEFI specification 2.3.1. And the goal of secure boot is that you don't run untrusted code on your machine. And this is done by verification of all those components started. And the basic idea is that each component verifies the next one before actually running it. So the firmware itself checks the bootloader, then the bootloader goes on checking the kernel you are loading. And the kernel, again, is checking any kernel modules or drivers you are loading into kernel address space and running it there. And all those keys used to verify the components are managed by the firmware. And that means for that to work, the firmware itself, the code living in the memory, and also the storage for the keys, which is flash usually, must be protected so that the operating system or any malware trying to infect the system can't modify this kind of stuff. And how we are going to implement this for virtual machines is the topic of this talk. So next one, QEMU, you probably know this one. It's an open source machine emulator and virtualizer. And it emulates all the stuff you find in your physical machine as well. You have the chipset, you have a timer, you have interrupt controller, all the stuff you need to interact with the virtual machine, a virtual graphics card, keyboard emulation, mouse emulation, and built-in VNC server you can actually talk to, QEMU. Storage, of course, network USB. Next one is KVM. That's the kernel virtual machine. That's a driver for the Linux kernel, which provides applications access to the virtualization extensions available in modern CPUs. On the x86 architecture, those are the VMX extensions on Intel processors and SVM extensions on AMD processors. On ARM, there's hybrid mode, and there are also other architectures supported by KVM. And QEMU will actually use KVM for CPU virtualization. That means the code of the virtual machine runs directly on the CPU, and of course, it's the fastest mode of operation you want to usually use. The other option we have with QEMU is TCG. TCG stands for Tiny Code Generator. It comes with QEMU, and it's usually used if you're running not on your native architecture. For example, if you're emulating an ARM guess on an x86 machine, then you can't run, of course, directly on the CPU. So TCG will translate your guest instructions into host instructions and run them. It can also be used to run virtual machines on all CPUs without virtualization support. And a somewhat strange use case is sometimes if you're running stuff on KVM, it's too fast, especially if you're running very old guests. There's one funny example, some old Windows operating system version. If you run it on a modern hardware on KVM, it's just so fast that the calibration loop goes so fast that Windows crashes with a division by 0. And the easy fix is to turn off KVM and use TCG instead, and then it works fine. Next slide. Next one, EDK2. It's a EFI development kit. It's a reference implementation from Intel for EFI. It lives on tianocore.org, and the source code is available on GitHub. More interesting for there's one. More interesting for QEMU is OVMF, is Open Virtual Machine Firmware. It's an EFI implementation for QEMU and actually lives inside the EFI development kit repository. It has drivers for the usual virtual hardware you have in QEMU, for VirtIO, for VGA devices. And the EDK2 repository had also the firmware for ARM. So if you want to play with that, it's also in this repository. CBIOS is the default firmware in QEMU. So if you start QEMU and don't say something else, you want to do this or that firmware, what you get by default is CBIOS. It's a classic BIOS implementation. And the main users are QEMU and also core boot. So if you have core boot on your machine and you need a BIOS interface, that's also the way to go. And while you can also run core boot as QEMU firmware, that works too. So that about all the terms I want to cover first. So this is where we have been 2 years ago. Open secure boot support is available in the EFI development kit source tree for quite a while already. It uses OpenSSL for crypto support, but doesn't ship it as part of the repository, so you have to unpack the tarball and apply a patch because some differences in the EFI environment. There's no standard IO, for example, so they patch all this out. And then you can just go build it with secure boot enable option, and you have working firmware with secure boot support. But the problem is the firmware itself isn't protected. The memory and the data storage of the firmware is not protected at all. And also the flash where the keys are stored and where the EFI variables are stored is also not protected at all. So the guest can do whatever it wants. That's still somewhat useful if you want to develop software with secure boot support, or you can still use this to verify you're using the interfaces in the correct way, but of course, that's not the real thing. So we want to go change this. So when designing QEMU support for something new, there are basically 2 choices you have. Also some in between, depends a bit. So One option is you stay close to real hardware, you emulate something which exists in the real world. And the other option is you create something new out of thin air. It's all software, it's all virtual. You can do whatever you want. And of course, both approaches have their advantages and disadvantages. If you go emulate something which exists, it's easy on the guest side because the guest will find some hardware, even though it isn't real, which it knows how to handle. So you don't have to deal with drivers. The guest operating system will be able to just use your hardware. And it also usually simplifies the management of virtual machines and physical machines if you keep the differences between physical machines and virtual machines small. On the other hand, it can be can also have disadvantages, depends on the kind of hardware, of course. One example is the old USB adapters, which are quite difficult to emulate in an efficient manner. It needs quite a bunch of CPU time. So it has been a problem for a long time that as soon as you connect a virtual USB tablet to a virtual machine, that it eats a lot of CPU time. Another problem is that you are limited to what the physical hardware you are emulating is able to do, which is becoming a problem these days with the serious graphics adapter, which is not the default graphics adapter anymore because of this. Because the serious VGA is a design from the 19th and it just can't keep up with today's needs. And so, yeah, you have to. So the other option is to create something paravirtual. It's the usual term for that. You have more freedom in designing things. You usually get better performance. If you're doing it in a clever way, you can get a lot of code sharing. For example, all the virtual devices for SCSI, for block, for network, for input, for serial devices, they all use the very same ring format to send data between host and guest. And you can also try to simplify things because it's a virtual machine. So some things are easier than on physical hardware. The backside is you, of course, have to write and maintain the guest drivers. It's not so much a problem for a US user. If you're using Linux, the drivers are part of the kernel, so you don't notice. It's more visible to the normal user on Windows because you need this special driver image with all your VirtIO drivers on it. And if you try to simplify it, can also backfire. If you simplify too much, it can create quite a mess long term. For example, the original VirtIO specification went on say, oh, we are a virtual machine. We have this. We know what endianness our architecture has, and so we just go with the native endian. So we don't have to bother with byte swapping. And that turned out to be not a good idea because these days IBM is pushing the PowerPC architecture to little endian, from which was historical big endian. And so the virtual machine usually starts in big endian mode for historical reasons. The firmware talks to your VirtIO device in big endian mode. Then loads the little endian Linux kernel, and the little endian Linux kernel, of course, will also talk to the VirtIO device. So the full concept of native endian just doesn't make sense anymore, especially for PowerPC. So that are the traps you can trap into if you're trying to simplify too much. So let's see how the firmware is protected on physical hardware. We have something called system management mode on all the processors since at least 20 years or so. And the chipset can set an interrupt to enter system management mode. And the processor will store the complete state of the processor in memory and start execution at a definite address. And with a special instruction, it can return to normal operation. It was designed for stuff like power management, that you don't need a special side processor to do your power management. You can just have the chipset rise and system management interrupts, and then it runs this special code, which can check the temperature sensor and maybe tune the fan speed and if it's too hot or too cold, stuff like that. And there's some memory which can only accessed in system management node. It's MRAM. It's pretty small, 128 kilobytes. It's a location where usually the VGA frame buffer sits. And newer chipsets have, in addition to that, a bigger section called TSEC. It can be up to 8 megabytes big, and it lives at the upper end of the memory mapped below 4 gigabytes. That's the upper end of the 32-bit address space. And the configuration for SMRAM and TSEC can be locked. So if once it's initialized, it can be tampered with until the machine is reset. So the question is, we are going to do the same on QEMU or something else? The advantage, of course, is we can hope to not have to write too much new code, because if you're implementing system management nodes in QEMU, we can use existing logbox code, for example, from the EDK2 toolkit. Performance shouldn't be that of a big issue. The problem is that system management mode was originally designed for something else, not for security. And so it has a pretty bad security track record. You can check the talks from previous Congress years about various attacks on system management mode. So we have to be quite careful if we go this route. Also, 2 years ago, we had no system management support in KVM. And TCG had at least some basic system management support. So we decided we go the system management route, and let's start looking at how it looks in QEMU. Our to-do list. QEMU can emulate 2 different chipsets. One is from the older one is from the mid-90s, and this is so old that it hasn't this TSEC memory. So we can't use this for secure boot because the EDK2 implementation needs more memory. It just doesn't fit into SMRAM. So this one is out. We have the newer Q35 chipset emulation, which you can, if you start QEMU, you can pick this with this -M Q35. And we have some SMRAM support from the basic TCG support already present back then. We have to complete it. We have to implement TSEC and also implement the lockbit support. So if you try to lock down the TSEC and SMRAM configuration, it actually works. And we also have to figure out how we are going to protect the virtual flash. One foundation we are building on is the memory API. It was created by Avi, that's the same guy who started the KVM project, and it was merged in QEMU 1.0, and it pretty much puts the memory management inside QEMU upside down. Before, older versions of QEMU had a very simple scheme for registering memory and MMO regions. You just register it and it stays there until QEMU exits. And if you register something else on the same address, the old what was there before just goes away. And now we have a hierarchy of memory regions, and you can enable them, can disable them, you can move them around, you can create aliases. And these regions are used to build address spaces, which was a big step forward in correctness of the emulation of various corner cases. For example, if you remap a PCI bar of your network adapter, for example, it now actually works correctly, that the bar actually disappears at the old location. This wasn't the case before we had the memory API. And another interesting one, which caused quite some bugs, is that each PCI device got its own address space for DMA. And if you don't turn on the busmaster DMA bit in the PCI config space, we also don't turn on this memory region, with the effect that DMA stops working. And there have been quite a few drivers, especially VirtIO drivers, which have never been tested on real hardware, which didn't set the busmaster bit, and this change broke those drivers. And implementing system management mode would have been pretty much impossible without this memory API. So let's have a look how this looks like. I think it's a bit smaller, so it fits. Yeah. There's a system memory region of the simplest machine type we have. It's an all Ether PC without any PCI stuff. But it's nice to see how this looks like. Here's the system region, which covers the complete address space. We have the memory, which is 128 kilobytes, I think. And then we have a container, which is a region which just holds the subregions for the server's VGA memory. And you can see what is visible right now is this one, because the other regions are disabled. And you can program the VGA bank registers to map some memory of the VGA memory into those two places. In that case, the region will be enabled, and it will be visible to the guest because it has a higher priority. Here's a priority, just priority 1. So this will overlap this low memory if it's enabled. There's then just the ROM area, there's a BIOS, and that's it for a simple ISA machine. So how it looks like for our Q35 machine. It's very similar. We have, of course, Q35 is PCI, so we have a lot of PCI bars, which I left out here to have enough space on the slides. We have the SMROM region, which was already there in older QEMU versions for this basic SMM support we already had. Which is new is this TSEC black hole. This overlaps the top of the RAM region, which is right here. It's the topmost piece of the memory, and it has a higher priority. So if your guest tries to access this address range, it will land at the black hole, and the black hole just discards any writes. And if you read from it, you will just get FFFF, nothing else. So that way we can hide the TSEC memory from the normal system view. Then there's also MMIO, MMConfig address space, IO APIC. And the Q35 chipset also has an SMROM alias at a higher address, which it's disabled because EDK2 doesn't use it, but the alias is there. And then we have the area for message signaling interrupts, and finally 2 address areas for the flash, where the Flash 1 is where the variables are living, and flash 0 is where the code is living. Come to that later in detail. To enable access to the system SMM memory in SMM mode, we have this SMRAM region, which has aliases into low and high SMRAM locations, and also for the TSEC, which refers in the actual memory. And then each virtual CPU gets its own address space. This one, and it's just these two, the SMRAM, which we have right here, and the normal memory. This is all the stuff we had on the previous slide. And if the CPU enters system management mode, this SMRAM alias will be enabled, and the CPU can access all these regions. And if it leaves system management mode, it's disabled again, and it's not visible anymore. And we have one of these address spaces for each virtual CPU. So it's impossible to run SMP attacks because each CPU has its private space. So you can't try to bring one virtual CPU into system management mode and try to trick the systems of that to get access to those memory regions with the help of another CPU. It doesn't work because each CPU has its own private view, and for each CPU individually is enabled or disabled here. We also have to care about PCI devices, and PCI devices get for busmaster DMA just a normal system view, which is basically the same CPU is seeing if it's not in system management mode. So you can't use your network card or a hard drive to access this memory indirectly. So we also had to implement the logbit support. This is a snippet from the test case. The configuration register has an open bit, which can be used to make SMRAM available even when not in system management mode, which is used for initialization. So the first part of this test case checks if the open bit can be set, and if you set it, it's actually open. And the second part of the test just sets the log bit. And if you flip the log bit to true, it will automatically switch the open bit to false. So it's closed and only on SMRAM is only available to system management mode. And it also flips the open bit to be read only, so you can't open it again until the machine is reset. And this log bit will also lock down the configuration for the TSEC memory. So the original Q35 chipset and physical hardware had a bug. There's a register which basically configures the memory split, how much memory is mapped below 4 gigabytes, how much memory is mapped above 4 gigabytes. And if you lock down, if you set the lock bit to lock down the configuration, the TSEC size and enable bit are locked down, but not this configuration register. So you can use this configuration register to just move away this protection and access the memory nevertheless. And that one is easy for QEMU to handle because we don't configure the memory splits this way. So this register simply doesn't exist in QEMU, and so you can't exploit it. And we do the memory split configuration with command line switches instead. And by default, you have 2 gigabytes of low memory, and everything else is mapped above 4 gigabytes. Next one is flash protection. where all the keys and variables are stored. We need to protect this one as well. And on physical hardware, it works that way that if you try to write to flash, it will be put in device mode, and it will also trigger a system management interrupt, and the system management interrupt will put it back into read-only mode. And it's pretty complicated. It's also prone to race attacks. There have been successful attacks to that. And because it's on physical hardware, you can't basically can't fix it. So newer versions of the chipset use even more complicated protocols to handle the races. And we tried to do this in a simpler way. First, we have two parts of the firmware. We have first the code, and second the variables where all the keys are stored as well. And the code is usually just read-only. The guest can't write it, and firmware updates simply happen by doing them on the host. So the firmware is just a normal distro package, and your normal distro upgrades will also upgrade the firmware, and QEMU will pick up the new version on the next power cycle of the virtual machine. And we have the second part of the flash, which stores the variables, and we can simply discard any writes which happen if you're not in system management mode. That's a concept we have borrowed from ARM. We have a secure flag, which is on ARM used to signal user space or kernel mode access, and on ARM it actually exists as bus signal. So the flash chip can see whenever the access comes from kernel space or user space, and can control access that way. On x86, this doesn't exist as a bus signal, but on QEMU, it's software, so we can just borrow this concept and use it on our virtual machines. It's implemented using memory transaction attributes, where, among other things, is noted where the secure flag is set or not set, and then the flash code can just decide, okay, we can allow this write or we can't. So that's a lot easier than on physical hardware. So this all works just fine with TCG, but we also want to run it fast with KVM. So we have to look how we are going to do that. We can't pass the memory regions, the hierarchy we have as is, to the KVM module in the kernel. So QEMU has to flatten the address spaces into a memory map, which is just a linked list of slots. This one is passed down to the kernel module, so the KVM kernel module knows everything it needs to know about the address spaces. And this memory map is used by all vCPUs. Each time the address space changes, it has to be updated. So we have the problem that becomes quite expensive on SMP machines. If we would take the same approach we have on TCG, that each virtual CPU gets its own address space, or in this case, its own memory map. So it has to be designed in a different way. KVM got support for address space IDs. So now we can pass down two address spaces to KVM, one for system management mode and one for outside system management mode. And again, these two maps we have now will be shared by all vCPUs. So adding more vCPUs wouldn't make things slower. We also needed a new I/O control to ask KVM to raise a system management interrupt. And also the KVM1 state structure got a flag for system management mode, so QEMU knows when an exit happens, whenever the CPU, which was currently running, is in SMM mode or not, because it needs that to set the memory transaction attributes correctly, so the flash chip knows whether the write is coming from system management mode or not. So these are the address spaces in KVM mode. They look a bit different. We have two of them to generate those two memory maps. One is the CPU memory, which is just a normal system view, basically, for if you're not in system management mode. And for the system management mode address memory map, we have the KVM SMRAM address space, which is basically SMRAM container very similar to the one in TCG mode with a higher priority and also with lower priority in alias to just the normal system memory. So that was it for KVM. And of course, we also need some support in OVMF in our firmware. So we thought, oh, that should be easy, because the intention of you doing the SMM way was to share the code and reuse the code. And the lockbox code is in the EDK2 repo, but all the code to create system management for initialization and also the SMM handler itself wasn't in the repository. So we run around, ask the Intel guys, which are maintaining the EDK2. And the first thing we got was a pointer to the Quark toolkit, which is a 32-bit chipset or reference design from Intel. And yeah, of course, only the 32-bit code was in there, which was a bit disappointing. And Laszlo, co-worker of mine, went through the code and found a security bug in there, which delayed the whole thing quite a bit. We had a lot of discussions with Intel, with the EDK2 maintainers, also with the Quark team and with the security team. The security issue wasn't handled very well by Intel. I'm not aware of any official security advisory for this Quark thing. But finally, half a year later, the code was committed to the EDK2 repository. And we didn't only got the 32-bit, also the 64-bit code. And the first committed version also had this security bug fixed. And the nice thing is, Intel continues to maintain this code in the open repository. So you see a constant flow of patches and improvements. So it's not an Android-style code drop. Just here, you have it, and now keep quiet for the next month until we have the next release. That's actually happening in the repository. And it's also the repository where they cut this development kit releases now and then for the OEMs for all the laptops. So the nice thing is, at some point in the future, you should be able to look at the code, which should be roughly what you are running on your laptops. So that's nice that we got this open sourced as part of this effort. So with this in place, it was as easy as we expected initially to get to implement secure boot support. It was still not trivial. There are a lot of little details you have to get right. But we got it finally merged 1 month after the initialization code was merged. So if you want to play with this yourself, you need QEMU version 2.5. Also Linux kernel 4.4 on your, which shouldn't be a big problem with a decent recent distro. libvirt support took a bit longer. It's in version 2.1, which is pretty recent. So it could be that you'll not have it on your distribution. EDK2 doesn't really do releases. So you can just pick the latest Git snapshot. In Well 7, we are using a snapshot fin mid of the year. And then this is how the libvirt configuration looks like. You need the Q35 machine type right here. Oops, that's a bit long. Can I make it fit? Yes, it fits now. If you don't want the default firmware, which is cBIOS, you have to specify this loader tag, which is called loader for historical reasons, dating back to Zen times. You say read-only because this read-only is for the code. That's read-only. Secure, yes, is for the variable store. Type T-flash is it's flash memory. This is a template for the variable store, for an empty variable store. And you don't have to explicitly add this one. Lib will store it by itself. Create a copy of the template and store it in var libvirt somewhere. And of course, you need system management support turned on, because it's turned off by default because it doesn't work in older versions. So if you want to use QEMU directly, it looks like this. Of course, you need again the Q35 machine type, and you have to turn on system management node. This creates the flash device, the first one for the firmware, for the code, which we set to read only, and the second one for the variables, which we put into secure mode, which needs to be done with this separate configuration switch. And then, of course, all your configuration arcs. One nice thing QEMU supports is that you can put command line arguments you want to add to QEMU. In this special QEMU tags, you have to import this special namespace in your libvirt config. And then you can add this one. It's very useful if you have a libvirt which is too old to have system management support. You can do it this way. Was created to make it easier for developers to work on new QEMU stuff, which isn't not yet supported by QEMU. You can still run your virtual machines you are using for development and testing using libvirt, because you can just tweak the QEMU command line this way. I'm running a Jenkins instance, which does automatic firmware builds, and it lives at this address. Each time something is committed to the upstream repository, it kicks a build, so it has updates quite frequently. It's an easy way to install the EDK2 firmware, OVMF. There's also packages for the ARM firmware, also cBIOS core boot, but the most interesting one is OVMF. There are 3 different variants. The one named Needs SMM is the one with system management support. And system management support is a compile time option, so that binary doesn't work without system management support. And it also requires Q35 because the older chipset just doesn't have a big enough TSEC. And the other ones, Pure AFI is just an AFI firmware which supports both QEMU chipsets. And the third one additionally has cBIOS compiled as compatibility module. There's little reason to actually use it in a virtual machine, because you can just use cBIOS directly. But if you want to play with this or test something which needs a compatibility module, you can use those. Okay, what's the time? Yeah, I think we have enough time for a short demo. Um, this one. Let's use this one. I can try. Okay, this. I think it's the device manager. Is it here? Secure boot configuration. I can look at it. It's disabled. And oops, I just noticed I missed the slide, but I can show it in the demo. Let's exit here. OVMF doesn't come with any doesn't come with any keys in the default key store, and the way you can add them is with a small ISO. You can see, can see it right here. This one is a ISO image attached as SCSI CD-ROM. And there's an EFI application which can be used to add the default keys. Oh. So it adds the keys and it enables secure boot support. And then we can reboot. And then it just stops. The reason for that is that the ISO image which enables secure boot isn't signed, and because it isn't signed, it isn't booted now anymore because secure boot is enabled. Oops, that wasn't. So I can just use this one. So let's kill this one. So you can see secure boot is enabled. And if you look, you can here see the certificates which are loaded by this enroll application. First one is a Windows key, and this, which Microsoft uses to sign the Windows operating system. The other one is the key Microsoft uses to sign third-party stuff. That includes Linux, Linux AV application, Linux bootloader application used by various distributions, and also PCI ROMs and stuff like that. And the Red Hat version of the ISO also installs the Red Hat secure boot key. So, okay, let's close it. Okay, that's the end. I didn't do this all on my own. Actually, it was quite a small part of it. I did most of the Q35 chipset implementation. Has also involved Paolo, which did all the KVM and TCG code. Paolo is current KVM kernel maintainer. And most of the work inside OVMF and talking to the Intel guys about releasing the source code for the SMM initialization was Laszlo. And I think he did most of the work, I think, at the end to get all this going. The slides are online on this link. You can also scan the QR code, it's just the link on the slides, to the slides. Cool, that's it. Any questions?
So if you have any questions, we have 4 microphones here, 2 on each side. Do we have any questions yet? Otherwise, I have a very quick question, kind of high level. Is there going to be support for, or does Secure Virtual Boot support things like containerization with C groups, or will it, or does it not, is it not even relevant?
I think for containers it isn't relevant.
Although there is a need for secure boot in that environment too, I would have thought.
I think we would have to take a completely different approach because you just don't have a virtual machine or you don't have firmware if you're running containers.
Are there any questions from the internet?
Unfortunately not.
Okay. All right. Well, join me in thanking the speaker for such a great talk.